This video will investigate relationships between linear regression and Anova. So when I do a linear regression t-test, my degree of freedom is equal to the number of points minus 2. My null hypothesis is that my beta 1 is equal to 0. Just a reminder, beta 1 equaling 0, this means that there is no slope to that relationship. So it's a test for linearity, seeing if there's slope. And the alternative hypothesis is that there is slope. So really, I'm testing two things. I'm testing to see if there is some sort of a slope and to see if it actually looks like a line. So this is technically two things that we're testing here by doing this one thing. After we do a linear regression t-test, if we have evidence of a linear relationship, it's often a good idea to follow this up by calculating r squared, because r squared tells us the percentage of our variation that's coming from the model instead of due to error. So percentage of variations from the model instead of the percentage of variation coming just from random error or a lurking variable. So I want to look at this in a little bit more detail as to what I'm really saying here. Wondering, what are we comparing to see if our line's actually a good fit? And the two things we're comparing are how close are our values and our predictions, and hopefully our values and our predictions are very close. Hopefully our line and our points are lining up almost perfectly. And the second thing I want to know is there a meaningful slope? So if the things line up perfectly but it's horizontal, well, that's telling me that there's not really a nice relationship between those variables. There's not a strong correlation going on with them. So let's just kind of view these things together. So this first one, how close are our values and our predictions? So one of my concerns with linear regression is that when I have my line, and reminder, my line is y hat, I'm wondering how close are all of my individual values y, and I'm gonna pause for a Fiona break here as she transitions over. Very good. And I'm wondering how close are my values? My values are my y's. And I'm wondering how close are these to my predictions? My predictions are my lines. So I'm comparing my y's from my data to the y hat from my lines. So this is looking at sort of the variation in all of these amounts that I could be off by. So I'm going to draw these things in. So this first one here, I have a certain amount of error, I have a certain amount of error, I have a certain amount of error, and so on. So ideally, this variation is small if it's actually linear, if I'm making good predictions. So my values that I'm looking at here are all of these individual y values. And I'm going to compare these to sort of the center line that I'm looking at here. Is my line of best fit is my y hat. So when I'm comparing these two things, I'm really calculating my residuals. And residuals look at errors. So when I'm analyzing this, I'm seeing what's the variation for my residuals look like, or what's the variation that exists within my data set. So this sort of comparison that I'm going to do is some sort of variation that's existing within my data set between my values and my predictions. And if I'm wondering, well, what would the degree of freedom look like for this? Well, I'm making a ton of little predictions here. So the total degree of freedom would be equal to the number of points minus 2. That's ultimately what I have going on with my degree of freedom when I did this linear regression t-test. It's pretty much the same thing. So having small errors would be great, but again, the other part of this is I want to make sure that there's slope. So the null hypothesis for this test, beta 1 equals 0, saying no slope, this would look like this. It would just be flat. And this flat line in particular would be in the middle of all of these previous y values. So this flat line would just be the average of our y's. So if our linear regression line is equal to the average of our y values, so if this is equal to our line, well, then there's no meaningful slope there. Now, if I find the average of all of my y values, and this is sort of the baseline where I'll compare all my predictions from. So here's the middle of my y's, and the middle of the y's and the middle of the x's, that x bar, y bar should always be in the middle of my regression line itself. This is one of the values that I use when I'm creating a line. If there's slope, I should see a difference, a substantial difference between this flat line and my actual line. And I switched the colors up on you there, sorry about that, but I hope you're still seeing from the picture what's going on. I have my flat line, and I'm comparing that to my actual line. And I'm hoping there's a difference between the two. So I'm wondering, is there a meaningful slope? Well, in this case, my values that I'm comparing, I want to look at my line y hat, and there might be many values on this line y hat, but ultimately I'm treating this like a single line here. And I'm comparing this to my center value of this y bar if it were flat. So this is looking at sort of the variation between my groups. So how much variation is there between my points? How much slope is there? My degree of freedom here, well, I only have two groups. I have sort of this line and this line. So my degree of freedom would be 2 minus 1, or just 1 here, if I were to try to think of this comparison. I'm going to talk about just one more element, and then I'm going to really play around with these ideas sort of in the abstract here. But already I'm sort of seeing some sort of a variation within and some sort of a variation between. I have sort of this gut feeling that this looks like Anova now. And the reason why I think this looks like Anova is I have a variation that I have sort of from all of these residuals. And I have the variation from the line itself. My hope is that the variation from the line is stronger than the variation from the residuals. I'm hoping that there's very little error and that there's a significant slope or significant difference between flat and not flat. So my hope is that if I look at the variation from the line, and I divide this from the total variation, the variation from both the line and the variation from the residual, that this is a large number. Because this would tell me where all of my errors were coming from and where all of my predictions were coming from. It would allow me to figure out sort of the percentage of variation accounted for by my model. I'm going to take all of these pieces that I have here, and I'm going to continue just kind of looking at this in an explorative manner. I'm continuing in the lesson 13 packet here. And here's just a scenario. I have a data set where I have my x values and my y values. My x values here, 1, 2, 3, 4. My y values, 4, 6, 8, and 6. If you were to use this data set, and if you did something like a linear regression t-test on it, you would end up with the line of best fit of y hat equals 0.8x plus 4. Other information that you would end up with, you would have a t-score of 1.1547. You would end up with an r squared of 0.4. So I'm just going to fill in some things into this table, and I'm actually going to make my table a little bit bigger. My x values 1, 2, 3, and 4. My y values were 4, 6, 8, and 6. So this is my actual y value. And let's look at my predicted y value. So plugging these x values into my line, I get the following y values for this next part of my grid. And I'm going to type these into a calculator, and I'll see what I get. So it looks like I'm getting 4.8 when I plug 1 into this equation, which looks reasonable. 1 times 0.8 is 0.8. 0.8 plus 4 is 4.8. 2, this would be 1.6 plus 4, so 5.6, and so on. And it gives me this. Now, if this thing was straight up flat, just for reference, then my flat line would just be the average of my y values. So let's see what that looks like. So adding up my y values, 4 plus 6 plus 8 plus 6. And dividing that by my 4 y values, if this thing were flat, I would see an average of 6, which looks pretty reasonable. So you can see how my actual y values appear to be different than this. There appears to be some variation. My predicted y values appear to be different from this as well. There appears to be some variation here in this data set. So this was one way for me to test for a difference, but it really does feel like I'm comparing sort of this variation within my groups, that variation within my groups being based off of my residuals, and this variation between groups that was comparing my flat line with the line that I have for my prediction line. So let's try doing that within an Anova setting, and just let's see what we end up with. And if it's close, great, and if it's not, that's okay too. So reminder, our variation within, based off of our errors, this was our MSE, and we found this by taking our degree of freedom times our variances divided by the total number of values minus the number of groups that we're working with. So degree of freedom, we found this by doing n minus 1. Our variances, these were value minus center squared over n minus 1. So if I just do a little bit of prep work, technically these n minus 1s cancel. So kind of a nicer way of writing this is the mean squares of the errors compare our values and our centers. They square them to make sure we don't end up getting 0. And it's divided by the degree of freedom. So for our problem here, we want to compare our y and our y hat, because this will give us our error. This will give us our residual. So in this case, just kind of matching things up, our values are individual y values, and they're centered about the line y hat. So I think this should look like the following. MSE, which is an SSE over DF. We should have the sum of our individual values. These are our y values. And I'm comparing these to our y hat. And I'm going to keep flipping and flopping between these pages because I just want to show you again that what I'm really doing here is I'm finding each of these residuals That's what this represents here. This is residuals. And I'm squaring these to figure out what's going on with the sum of the squares of these errors, the sum of the squares of the residuals. I'm going to divide this by the degree of freedom. The number of values that I have are the number of points. I have 4 points. The number of groups I have, 2. So in general, what I'll have for this denominator, I believe, is going to be the number of points minus 2. Let's see what this looks like in action. So my first value was 4, and I predicted it should be 4.8. That had an error of negative 0.8, and I'm squaring it. My next value, 6 minus 5.6. So my next residual was 0.4. My next residual after that was 8 minus 6.4. Looks like a considerable amount of error there. 6 minus 7.2. And I had 4 points minus 2. I had a degree of freedom of 2. If I type this into my calculator, and I'll do so now, great. Okay. This gives me, for the top of this fraction, 4.8. And for the bottom of the fraction, that gives me 2. So doing the division, I end up with a mean square of my errors, a mean square for these residual squares of 2.4 or so. So just kind of listing things up, the top of our fraction was 4.8. The degree of freedom there was 2. In general, this looks like it's going to be the number of points that we have minus 2. And the mean square of the error looks to be 2.4 or so. And my mean square of the error appeared to be the sum of my residuals squared over the number of points minus 2. The same degree of freedom I had when I was doing my linear regression t-test. That's just showing up again. Second type of variation I had for Anova was variation between values. Now, this one is a little bit more abstract, so let me draw this picture here again. I have 2 things that I'm really comparing for my value. One thing I'm comparing is my actual line for making these predictions. And I want to make sure that this has slope, that it's not flat. So I want to compare this to my flat line that kind of goes through the middle of everything, this flat just y bar line. When I found the average of all of my y values, my flat line in this case is 6. So I'm wondering how much do my predicted y values, my y hat, vary from this 6? So kind of setting that up here as if this was a mean square comparing groups, let's see what this would look like. I'm going to have the sum of all of my individual values here, where I'm going to be taking each of these y hats, subtract this y bar, and when I'm doing this, I'm just figuring out how far apart are these things. And I'm going to square this, and I'm going to divide this by, well, I have 2 lines that I'm kind of comparing. So the degree of freedom here, 2 minus 1, I'll be dividing it by 1. So let's go through this together here for our data set above, and let's see what that looks like. So my first y hat was 4.8. And I'm comparing that to the average of my y value, 6. So my actual line compared to a flat line. I'm going to square this so I don't have any issues with my negatives. I'm going to look at my next predicted value, 5.6. And I'm going to compare this to my flat line, 6. And I'm going to square it. Next one, my next line value, predicted value is 6.4. My flat line is 6. And finally, my last one is 7.2. And my flat line, again, is still 6. When I'm dividing this out, I'm dividing by 2 minus 1. I have 2 lines, so my degree of freedom for these 2 lines that I'm comparing should be 1. So I am comparing the variation between our line and a flat line. I want to see if there is slope. I'm going to type this into a calculator and see what I get. Okay, great. So for the top, I got 3.2. And for the bottom, I got 1. This will always be the case. So the bottom here is always going to be 2 lines that we're comparing, so 2 minus 1 or 1 for that degree of freedom. Our sum of squares of comparing these 2 treatments is 3.2. And dividing this gives me 3.2. So this MST is the sum of all of our line values minus our flat average of our y's squared divided by 1. So since it's divided by 1, I don't even really need to have that. I could just have the top of this. I am literally comparing our line to a flat line because I'm curious if there's going to be slope. So comparing variation between and variation within, sort of matching this up with the way that we used to do Anova. F is the MST divided by the MSE. Let's see what we get when we do this. So I am taking my MST was 3.2. My MSE is 2.4. This gives me 1.33 repeating. If I wanted to find the p-value, I could do FCDF, 1.33 repeating, comma infinity. Anova is always a right-tailed test. My degree of freedom, I'm checking to see if there is some sort of slope. I'm checking to see if there is minimal error. So I'm really kind of doing 2 things at once here. So in this case, I had 1, 2. Let's see what this gives me. So I'm doing my FCDF, 1.33 repeating to infinity, 1 for my first and 2 for my second. This gives me a p-value of 0.3675 or so. So that's a pretty large p-value. So this is telling me in the context of this problem that I probably want to fail to reject the null hypothesis. And if I'm failing to reject the null hypothesis, when I'm comparing my groups here, this tells me that I failed to tell the difference between y hat and y bar. In other words, I do not have evidence that my y hat and y bar are different. I don't have evidence of a linear relationship. If you were to do a linear regression t-test, you should end up with the same p-value. And if you remember the relationship between t and f, let's just check that. It should be the case that t squared gives us our f in general. Let's see if this actually works for these particular numbers. It'd be incredible if it does. This means that I would have an Anova way of doing linear regression. Our t-score was 1.1547, and I did linear regression t-test. And when I type this into a calculator and square it, great, I get 1.33 repeating, which is exactly what I had for my f-score, So things are matching up kind of the way that I would hope they should. Now, the other component back on this first page here was my other hope was ideally most of the variation was coming from the line instead of having variation come from these residuals. So let's try to figure out what's going on with this number. So I'm going to take the variation for the line, my variation, my SS for my T. I'm going to take the variation of my line, and I'm going to take the variation from the residuals, and I just want to see number-wise what happens when I kind of compare these things. So the SS of my T's, this was 3.2. 3.2, great. The SS of my E's was 4.8. 4.8. So I'm seeing I have 3.2 of my variation is kind of coming from the difference between these lines, but 4.8, a considerable amount of that variation is actually coming from my residuals. So this tells me that this looks like it would be a really, really weak relationship. Let's figure out exactly what this number is when we type this into our calculator, this SST divided by SST plus SSE. This is telling me something about how good my fit would be. And when I do this, I get 0.40. Now, if you happen to have linear regression t-test up on your calculator already, you may have noticed something. This is your R squared. So when you take the SST and you divide it by the SST plus the SSE, this is giving you a way of finding your R squared, the percentage of variation that's coming to you from that line here. So in fact, linear regression and Anova are really just kind of two sides of the same coin, but that might not be immediately obvious. Let's try taking another look at this and seeing what's going on with the relationship between the two, but I have a little bit of summary between them. So Anova and linear regression. You can either perform a linear regression t-test to check for linearity, or technically, you could use Anova to check. My mean square of the treatment, this is telling me how my predictions vary. And what this is comparing is sort of my line of prediction of what it would actually mean if I had some variation in my data set, and this flat line y bar. So variation between, this is really checking what's going on with the slope. My variation within is the number of values minus 2, the number of points minus 2. And this was looking at, here's my predicted line, and here are my y values. This is looking at the variation within my predictions. And it wants to know, well, how far off are all of these individual y values, your actual y values, from this line that we're using to make predictions? So what the heck is going on with the residuals? And Anova sort of compares the slope and the residuals to tell us if there's a meaningful relationship between these things. And R square ended up being the sum of the squares of the treatment, sort of this, what we're hoping most of our relationship is coming from slope. And we compare that to our overall variation coming from both our slope and our residuals. So I just want to show you kind of the two situations that can happen and see if they match up with what we hope would happen when we have a test for linearity. So for a test of linearity, my null hypothesis is that it's not linear, that it's flat. And my alternative hypothesis is that it is linear and that there's some sort of a mean slope. So looking through this, how will our y hat and y bar compare? So let's see what happened if this was not linear. Well, if it was not linear, I would experience something like this. I'd have a cloud of points, and my line would go through this cloud of points. and the middle of my y values, my flat line, would also be the same sort of middle equation here. So my y hat and my y bar, my line and my middle, would be really close to one another. This would cause my MST, which my MST compares my line and my middle, to be really small. There's almost no variation between these things in this situation. Now, unfortunately, the reason why that's probably the case is it looks like I have a ton of error. So my individual y values compared to my line, this would be pretty far apart, which means my MSE, which measures how much these things vary, how much error there is, would be pretty large. My F score, which takes this MST divided by this MSE, would have a small number divided by a large number. So I would have a small F score or ratio when I'm experiencing something that has a lot of error and does not look like a line. In this situation, if you had to choose between these options, you would hope that you would fail to reject the null hypothesis because we don't have evidence of a linear relationship. Going back to the shading for the F distribution, if I have a small F score and I shade to the right like I normally shade to the right for Anova, I would end up with that large p-value as anticipated. Let's see what would happen if we had a good prediction and what would go on with our MST and our MSE. So if this was a good prediction, then here's my line y hat, and the middle of my y values, if it was flat, would look like this. And there would be considerable difference between these things. My line and my middle would look substantially different. So there would be a large variation between my line and my middle. Now, if I have a really good fit, not only would I see that this thing has some sort of a slope, I would also hopefully have all of my points be close to the line. Linear regression kind of measures two things. It checks to see if there's a slope, and it checks to see if all of my errors are pretty small. So if this is a good prediction, I should also have a small amount of total error. If I have a large number divided by a small number, my F ratio should be large. And checking to make sure that this will match up, and hopefully will reject the null hypothesis as before. If I have a large F score and I shade right, this will give me a small p-value. If I have a small p-value, I would reject the null hypothesis, and this would tell me that I have evidence of a linear relationship. So this is the same sort of comparison that I made when I was working with Anova, but I just wanted to show you visually what this comparison looks like in the terms of linear regression. So if you have a small F score, that tells you that you have a lot of error and it looks flat. If you have a large F score or a large F ratio, that tells you there's slope and your errors are small in comparison to that slope. So I would like you to pause the video for this next one. I've given you a data set, really small one, 1, 2, 3, and y values of 5, 7, and 12. And I want you to first do some linear regression t-test here to get a baseline. Null hypothesis is that the slope is equal to 0. Alternative hypothesis is that the slope is not equal to 0. And I just want to know what the t-score, p-value, and r squared looks like for this relationship. And then we'll try doing the same thing with Anova. but just go ahead and pause real quick to try this linear regression t-test to see how close you are for the first of the two ways of analyzing this data set, and then we'll look at the second way together as well. So when I did this, I ended up getting a t-score of 4.04 or so. And I ended up with a p-value of 0.1544. Now I think this is interesting because if you looked at this t-score, you might think, hey, this is a pretty large t-score. Why are we ending up with a p-value where we would fail to reject here if we have this large of a t-score? And the issue is we don't have that many points. So we don't have that much evidence of this linear relationship. This could just be a fluke. I only have 3 numbers so far. So when I was doing this, I only had a degree of freedom of 1. It's probably going to take more evidence to really convince me that this is actually a linear relationship and not just normal variation. Now the R² for this ended up being really strong. It ended up being something like 94.23% or so. So what this is telling me is even though I had what seems to be a small amount of error, I still don't have enough evidence with this minimal amount of data set to reject the null hypothesis to say that there's a linear relationship. My hope is that I'm going to detect some of these same things when I do the Anova test here. So let's look at Anova. And for the null hypothesis, I'm just going to write this in words, if that's OK. So the null hypothesis would be that my prediction line and my flat line look the same. So my null hypothesis is that my y hat and my y bar look the same, that my average of the two is similar. So null hypothesis for Anova is that the average of one thing is equal to the average of another. That's kind of what I'm doing here. I'm wondering if the average of my y hats is like the average of my y bars. These are the two things I'm ultimately comparing. And my alternative hypothesis is going to be that they do not look the same. And if not looking the same is good. Not looking the same means they're linear. And now I'm going to pause the video as I give you time to calculate both the mean square of the treatment by looking at the sum of the residuals and comparing the lines. So the mean square of the treatments takes the y hats. It takes the line compared to the middle. And the mean square of the errors, this is the residuals. It's the y's minus the y hats divided by the number of points, take away 2. And again, I'm going to pause the video and give you a shot at this. Compare, so maybe add to this table here, find the y hats for each of these x values, find the average of the y values, and compare the predicted y values to the middle. And for this part, I already have the y values, so compare the y values to the predicted y values. And again, pause the video and give that a go. OK, and I added a little bit of scratch work on the bottom to keep track of these things. So when I'm comparing my line to my middle, I started by finding the middle of the y values by adding all my y values up, 5 plus 7 plus 12, divided by the number of y values, 3. This gave me an average y value or a center line. If this thing was flat, it would be flat at y equals 8. So I'm wondering how much will my line vary from that? Next thing I'm going to do in my scratch work here is figure out what all of my predicted y values look like. I'm using my line of best fit, this 3.5x plus 1. I'm just going to plug in each of these y values. When I plug in 1, I have 1 times 3.5 plus 1, 3.5 plus 1. That gives me a predicted value of 4.5. When I plug in 2, I have 2 times 3.5 is 7. 7 plus 1 gives me a predicted value of 8. These predictions are looking close. I'm off by a half. I'm off by 1. For this last one, when I plug in 3, I have 3 times 3.5, that's 10.5. 10.5 plus 1 gives me a prediction of 11.5. So for the variation between groups, if I'm comparing how much these things vary, my line compared to my flat value of 8, I would take the first predicted 4.5 minus the flat line 8. And I'm going to square this so I don't have any sign issues. I'm going to take the next one, 8, minus 8. That is the middle. Next one, 11.5 minus the 8. And when I do this, I end up getting a mean square of the treatment of 24.5. And that seems like a pretty large number to have for a variation between groups. Usually a large variation between groups means that you have evidence that something is linear. We're going to hold on to that thought, though, because again, you have a really small sample size, so it's going to take a lot to convince me. MSE. This is how much error I have between my values and my predictions. And I can see I have an error of 0.5, an error of 1, and an error of 0.5. So I'm really looking at all of those errors squared. And my degree of freedom for this thing is going to be the number of points, in this case 3, minus 2, gives me a degree of freedom of 1. And this matches up with my degree of freedom for my linear regression t-test, and it always will. The first one always will have a degree of freedom of 1. It doesn't even have a denominator there. You're just looking at the differences. So for this one, I'm taking my first y value, 5, minus my predicted was 4.5. I was off by a half, and I'll square it. Second one, I was off by 1, and I'm squaring it. Last one, I was off by a half, and I'm squaring it. And I'm dividing this by my degree of freedom. My number of points minus 2 in this case is just 1. When I do this division, I end up getting an MSE of something like 1.5 or so. So calculating my F, taking my MST divided by my MSE, my variation between, divided by variation within, I'm going to have 24.5 divided by 1.5. And this is appearing to give me 16.33 repeating. How do I know if this is reasonable? Well, let's do our quick check. If I take my t squared, this should give me my f. So if I take 4.04 in my calculator and I square it, I get approximately 16.33. Already things are checking out reasonably well. Next thing that should match up is the p-value, though. So my p-value is FCDF. It's a right-tailed test. It starts at 16.33 repeating, comma infinity. And this is a really, really large f-score, but your degrees of freedom are pretty small. They're 1 and 1. When I type this into my calculator, FCDF 16.33 repeating, comma infinity, 1 and 1, it looks like I get an FCDF of something like 0.1543, which up to a little bit of round-off error is pretty close to my old p-value. Again, I have a really small sample, so even though I had a large f-score, even though I had a large t-score, this was not enough evidence for me to say that this thing looked linear. But looking at the predictions look strong. So hopefully this is still giving me a strong R squared, even though it's a bit too soon to use it. So let's check that out. Let's see how much of our variation is coming to us from the line, and how much variation is coming to us as a result of the error. So we're going to compare the MST to the total amount of error, the MST and the MSE. Now, this seems like the most intuitive way to do it with the MS and the MSE there. In practice, This ends up mathematically working out for the SS instead of the MS. But in this case, this won't matter because these are identical numbers. But I'll take my SST over the SST plus the SSE. The SST, the amount I'm getting from my treatments, is 24.5. And the total amount of variation I had was 24.5 and 1.5 was 26. Taking 24.5 divided by 26 gives me 0.9423. This gives me my R squared. So this process of using Anova can be used to calculate this F score by hand instead of relying on technology. It also gives me a way of calculating my R squared by hand, assuming I have my line of best fit. So this is just sort of an intro to the relationship between these. There are deeper relationships between all the distributions we've learned throughout the term, but I hope this gets you excited to analyze some of those other differences.